What do we got? Just shout them out. Maggie. 9. Okay, pause. Anything before 9? 3. 6. Anything before 3? Okay. Let's go 3, let's go 6, and let's pick up because I hear 8 and 9 and 10 and other ones. And more. I won't remember them, so let's not even try. I have my graphing calculator out and open if it's something that we can use it in, but number 3, we don't need a graphing calculator for. So number 3, let me get there. Do you guys see this is a simple conversion? Pause. Will simple conversions be on the AP? Probably not, but could it be a part of getting to an answer? Definitely. So I don't think this would be a multiple choice. It's way too easy, but it could be necessary as far as, anyway, let's keep going. Being able to convert could be necessary in some of the AP type calculus questions. This isn't a calculus question though, right? It's pre-cal. You guys have options. One option, I always come back to a triangle, and I think that should be a key. It's in an endeavor card, true? In that we have r, we have theta. So couldn't you technically get cosine by adjacent over hypotenuse? Couldn't you technically plug in and say, wait a minute, I know who that is. I know that's x over r. I know who sine is. Sine is y over r. Even if it's not one of your typical conversion formulas, just go to the triangle and start plugging in. And why am I saying that? Guys, can't we multiply by, it's a little bit gross. If you don't like it, we could multiply by r over r to simplify our complex fractions, because then wouldn't we get r over 3x minus y? We're doing okay with math? We combine, and then the r cancels, and I brought the r to the top. Can't I then multiply and divide and get 3x minus y is equal to 1? I'm doing the algebra fast, but are we okay-ish? Yeah. Another way of doing it, if you want to see, if you saw it, you could have just brought that to the other side and had 4r cosine theta minus r sine theta equals 1. Wouldn't that be 4x minus y equals 1? Wait, my 4 randomly became a 3. I am so sorry. I got sleep last night, but my body's still recuperating from the past month. So, weak. Is that okay? So my brain would have done that, but I was afraid your brain wouldn't have done that. So I was like, oh, well, if you're looking, just go to the triangle, and then both ways work. I heard number 3, and then I heard number 6. Am I missing anything in between? Okay. So with number 6, guys, there's an endeavor card for this, true? How do we find area in general with polar curves? Isn't it 1/2 from theta 1 to theta 2 r squared d theta? Okay, and r needs to be in terms of theta, true? Okay, so, I mean, I even hear some of you guys in your chapter 11 tests where I'm supposed to technically have corrections from, and it should be turned into the folder to the front, and some of us fell behind, and I'm honestly not even thinking about grading them right now, but we need it eventually. But couldn't this packet and chapter 11 answer some of the same questions? Most of us know that we're supposed to get this into this, true? Yeah. Isn't the dilemma these? Mm-hmm. Right? The area inside the polar curve, and this is not a graphing calculator question, true? So could it be helpful to know that this is a 3-petaled rose? True? And if we knew it was a 3-petal rose, could we theoretically, if worst came to very worst, and I know, some of you are like, I don't have time for whatever. If worst came to very worst, couldn't you just be like, what's my 3-petal rose and when do I get it? Because what do you need? The beginning and the end. And if you know the beginning and the end, maybe that's one of the answers, or maybe they did one of those nasty 1-petal times 3 symmetry weird things. Either way, it might be helpful to know what and when and how this occurs. So I see a cosine, I see a 3. Cosine is nice when it equals 1/2, and cosine equals 1/2 at a pi over 3, right? But here's the dilemma. When's a pi over 3 going to occur? Careful, 3 times 3, Mag. No. We all do it. You guys have seen me. I just made a 4 into a 3. Pi over 9. So can't I do a pi over 9, which is going to be a pi over 3? How about a 2 pi over 9? Hey, that'll be a 2 pi over 3. Oh, what was in between? Oh, stink. I don't mind pi over 2's either, do I? Pi over 2's. There's our pi over 6's. Wait, I don't mind zeros either. Okay, well, I know it could be nasty. to get it, but maybe it's worth it. I could plug in 0, no big deal. Cosine of 0 is equal to 1, true? I could plug in pi over 9, because that would be cosine of pi over 3, which would be 1/2, true? I could plug in pi over 2, pi over 6, which is going to be pi over 2, which is going to be 0. I could plug in 2 pi over 9, which is going to be negative 1/2, because I'm now in the second quadrant. I could plug in pi over 6, which is going to give me, sorry, one sec, I got lost somewhere. 2 pi over 2, does that give me pi, which is negative 1? Sorry, no, it gives me 0, doesn't it? It gives me 0, I'm not negative 1 yet. Because it's a pi over 2. And I could go, where am I counting? Pi. So I was right. I lost a 0 somewhere. Did I lose a 0 somewhere? Oh, no, I didn't. I'm just not counting right. Okay, thank you. Going by pi over 6s and pi over 9s. The next one would be a pi over 9, right? 3 pi over 9? Which would be... Just kidding. They're the same point. That's awkward. 4 pi over 9? 3 pi over 6? Can we just make a picture at this point? I'm making a picture. So, what do we have? I have my 1/6 pi would be there. Yeah, don't worry, I'm getting there. There are my 6s. If I cut into 9s, that would be 3s. So wouldn't that be 1/6 would be less than 1/9? 2/9 was in between these two, right? Which would be here-ish. 3/9, oh, is pi over 3, which is the same as 2 pi. Oh, yeah, we just saw that. So that's our 2 pi over 6 and our 3 pi over 9. Yeah, it's nasty. So what do we have? 0 is 1. Pi over 9 is 1/2. Pi over 6 is 0. 2 pi over 9 is negative. Oh, so it's going the other direction. Negative 1/2. 2 pi over 6 is negative 1. Okay, so I had this. No, I had this. Then I had this. Oh, I see it. Do you see it? It's half a petal, and it's half a petal, and it's going to come in and be half a petal, and then it's going to go out and have half a petal, and then it's going to come in, and then it's going to finish it off. Okay. So with that, we don't need to have it all. Didn't I just say this is half a petal? What was that? That's half a petal. So hold on, how many petals do I need in total? 3. And if that's half a petal, can't I multiply this by 6? Half a petal times 6 will give me 3. True? Or if you want to think about it, I can take my half a petal from 0 to pi over 6, and I can double my half petal to get 1, right? If that's helpful. So I can double my half petal to get 1, and I have my cosine of 3 theta squared, and I need how many petals total? 3. So I can say times 3. So that'd be there, and then we have there, and then we have there from 0 to pi over 6. And now we have to see which of these are equivalent. Maybe they have my exact one, or maybe they've written it a different way. So checking it out, oh, they have mine. Hey, it's A, I'm done. But could they have possibly gone 1/2 the entire cycle? Yes. If this is half a petal, I know, and we have 6 half petals to make 3, couldn't I just multiply this by 6? So in pi, my period will be 0 to pi. I'll have the entire thing. So you could go through and he's not squared. Oh, but if he was, he would have been the right answer, and they could have tweaked him. I know. It takes time. It takes experience. But if worse comes to worse, I went to a table. Justin?
So can you re-explain how you knew that was 1/2 a petal?
It was all from me knowing how polar curves work. So when it went from here to here, I was like, oh, booyah, there's my 3.
Okay. So, like, since it starts at 1 and it goes to 0.
That kind of gives you a hint that it's half the arc.
And
It's
also,
not a 0 to a 0.
for C, I was kind of confused because doesn't that, like, encapsulate
Twice. Twice. Because it'll complete in pi. So 2 pi, it'll go around 2 times. And remember, it's accumulating area the whole time. You get it? Yeah. No, good question, though. They made these tricky because it's like, oh, yeah, that's the period. Oh, yeah, but it's squared. And then that doesn't have a half in. That one, actually, the negative pi over 6 to pi over 6 would have gotten it. The negative pi over 6 to pi over 6, except it'd be 3 over 2. Thank you, thank you, thank you. Took me a second. It's 1 whole petal, 3, and then the formula has a 1/2. Whew, they might have gotten me if I had thought too closely. Yes. Yeah. So, I mean, if it helps you, this would have been a 1/4 to be right. This one would have needed to be a squared to be right. This one would have had to be 3 times 1/2, because 3 petals, but the 1/2 are squared, because that one's 1 whole petal going negative pi over 6 and pi over 6. And this one would have had to have been the 1/2. Polar. I went to a table. Okay, sorry. That was 6. Good question. 8? Riley, was that yours?
Yeah. Oh, Maggie.
Oh, did you get it?
Yeah.
Does anybody else have 8? We okay? 9?
Yes. 9, 10, 11.
9 has a graphing calculator, so we need to figure out how to use it strategically, right? I have my graphing calculator ready. Are we in polar mode? I'm not. I'll get there. Can I come over here? Okay. I'm going to go ahead and I'm going to get my mode in polar, and I'm going to graph this dude. Let me see if I can zoom in on him and if I can half screen him. And if I can half screen him. Roughly. So I have 2 minus 2 sine theta and 2 cosine theta. Okay. So I have got him. 2 minus 2 sine theta and 2 cosine theta. 2 cosine theta is going to be like a 1-petal circle that's off to the side, and that's going to be a limacon with a cusp because the 2 and 2 are equal. Doesn't mean you have to know that, just, I don't know, for my purposes it helps. Zoom standard, there's my cuspy dude and there's my circly dude. I'm going to go ahead and zoom in to make my life easier. There's my cuspy dude, there's my circly dude. And no lies, I'd really like this to be just a little bit more that way and a little bit more that way. Okay. P.S. I just made up those numbers. I just wanted it tweaked a little bit. So they're asking for inside. You guys need to know enough. Well, you could watch it graph too, though. He's my little cusp dude, my little heart. And then he's my little circle dude. So inside the heart, but outside? But outside. Okay. So let me do this. Ooh, we have the question somewhere else, true? All right. Do you guys see how it's all of this?
What did they want?
That was the calculator. It's like, what?
Yeah, I was like, what?
It's like, what kind of line is that?
So much judgment. Didn't it say inside the limacon but outside the circle?
Yeah.
Am I wrong on that? Okay. So doesn't that mean that...
Oh boy. Whoa.
Uh-oh. Do you guys see where it's going to get rough? Right here. Didn't I just cover up some of that stuff that's inside the circle? Don't I have to subtract some of the stuff that's inside the circle? But how was I for all of this? Was the circle even a part of it? Okay, so I need to do like this plus this minus this. If you're thinking about the shapes. Because I can't have, oh, but wait, isn't there some more up here that's inside and outside? Oh, okay, well that makes it actually a little bit easier, doesn't it? Because check it. Don't I just need to do minus? Oh wait, no, that's the circle. Dang it, did I just get that wrong? Oh, that is the circle. My bad, I was right the first time. Lo siento. I lost my shape. Okay, so this part. There we go. That part plus that's the circle. Got it, got it, got it. Plus that part minus that part. The 3 cosine theta? I don't know, maybe it's an ellipse, but yeah, it's something like that. Okay. So this is these are both my limacon, right? Yeah. And then this is my 3, was it 3 cosine theta? Yeah. So I need to figure out my bounds. Basically, I need a half circle, and then I need a half of this graph, and then I need all of this guy, but not this portion, because this portion is inside the circle. Chili powder, hey, AB, whatevs. One of these days I'll get Mrs. Christensen to fix this. Okay. I know. It's been a while since we did that, huh? All right. I know I'm taking time, but this is a good question. All right. So what are we doing? A lot of you guys are trying to think about your bounds, true? There are a few different ways of doing this, to be honest. As far as right now in this problem, the simplest way, I think for my purposes, would be to know when this one starts and when this one ends. And guys, when does the limacon start and end? At zeros. Which is going to be when sine equals 1, right? Subtract the 2, divide by a negative. So sine is going to equal 1 at pi over 2. Careful. 3 pi over 2? Don't we have to go back to pi over 2 again? Should be 5 pi over 2? Am I crazy? How can we use our graphing calculator to help us? Because some of you are like, I have no idea how to use my graphing calculator. We need sine to be positive 1. Isn't sine positive 1, then negative 1, and then not positive 1 again until it goes around? Do you guys know that even though we can't do a lot, we can do trace? Can we plug in pi over 2? Oh, hey, it's at 0. Can we plug in, like, I'm hitting the trace button. Can we try 2 pi? Well, that's annoying. Why? Am I not including 2? Oh, I haven't included 2. Do like 4 pi, then we can see a little bit better. And some of you in Polar, remember how I said it might be helpful to have that little circle dude? So then we can see where everybody is, when everybody is. And to be honest, it might also be nice to be in simultaneous mode so you can see them graph at the same time. Check it. We can see them. See how they're graphing at the same time? P.S. I just hit my enter button to pause it, and I'm going to hit my enter button to restart it. Pause. Do you see how the circle just completed 2 rotations, and this guy's only here and hasn't made it back to there yet? And now he's going to go hit 0 again? So, I think that tells me some stuff, right? Now you could totally check on what you're doing as far as your window. Meaning, if I was to do my window just to be 2 pi, I got him. That's at pi over 2. And then he keeps going. There we go. Oh, wait a minute.
So they intersect at 0.
First one completes in pi, and the second one completes 2 pi.
Mm-hmm. Well, here's another way of looking at it. Do you see how this guy started over here? Mm-hmm. That was from 0 to pi over 2, and then pi over 2 to the rest of 2 pi. It's not going to hit 0 again until it goes again pi over 2, and then it comes back. So we don't want this portion of the limacon, do we? Because he's inside both. So we want to take away the 0 to pi over 2. We want the pi over 2 to the 2 pi. But if we do the pi over 2 to the 2 pi, what did we just include that we don't want? This part of the circle. Oh, okay, so maybe it's not as bad as we thought. Maybe when we go ahead and solve, maybe all we need to get both of these guys together is to go from pi over 2 to 2 pi of my 2 minus 2 sine theta. Careful, what's my formula for area inside a polar? 1/2, right? But then if I do that, I've gotten all of this guy, and I still need to take away that circle in order to get that area of inside the limacon, but outside the circle. I need to take this guy away. So there's going to be a minus. And so, hold on. You guys were thinking through the bounds with me, true? So this is 0 to 2 pi. This guy's gone around twice, right? So it's up to you. I just need to get out half of that circle. So what's half of that circle? Well, it finishes in pi, so can't I just go 0 to pi over 2? And that's half of them, and it'll take it away? I mean, you could make it pi over 2 to pi, or pi to 3 pi over 2, or 3 pi over 2 to 2 pi. I just need a quarter of the circle, because if this finishes twice in one hole, it's going to finish once in 1/2, 0 to pi. So all I need is take away a half circle. So at the end of the day, I think what we can do, meaning I know I'm not perfect, but I'm pretty sure I'm right, is to go from 0 to pi over 2 of my 2 cosine of theta squared d theta. And the nice thing is, praise the Lord, we have a calculator, right? So then we can go ahead and, has anybody plugged this in yet to see if we're good?
I'm doing it right now.
Okay, so will I. So we have my 0.5. You guys know your shortcut alpha window, right, to get your function integrate? From 0, no, just kidding, pi over 2 to 2 pi of parenthesis 2 minus 2 sine of theta. Make sure that you square the whole thing, right, guys? D theta. I do it all in one shabam, that way I don't mess up something or forget something, especially in multiple choice answers. Then I have a 0.5 times function integrate from 0 to pi over 2 of, careful, parentheses, square everything, parentheses, square everything. It's 2 cosine, right? Oh. We're okay. We can fix it in one quick little adjustment. Guys, what's the question say? Am I just doing inside one, outside the other? Or am I only looking at a certain quadrant? Ugh, sorry, guys. Struggle. Easy to forget something, right? No, we're good. So if it's fourth quadrant, what do I just not need to consider? Forget this dude. Right? Forget him. I don't need him. All I'm looking for is right here, and right here is blue minus black. So what do I change? I don't want to go from pi over 2. Hold on. It was 0 to pi over 2 to... No, 5 pi over 2 would get me all the way back. Here's 2 pi. Here's 0 to pi over 2. Where do I need to end? 3 pi over 2? If you want to, you can always double check it too, right? We could go back to our graph and we could say, hey, where are you at 3 pi over 2? Yeah, it is. See, you double checked. We're good. So forget that. All you need to do is change this guy to be a pi over 2 instead. A 3 pi over 2 instead.
Oh, so from 2 pi to 3 pi over 2?
Yes. The other way around in saying it, but yeah. Hey, do you guys realize that I have this whole line of code that I'm like, oh my goodness, wasting time? You know how to get to the front and the end of code, right? Do you guys know that second this way takes you all the way to the beginning, second that way takes you all the way to the end?
Second what?
Beginning of the line, end of the line? I learned it last year. I know. Because I was like, oh, I have to get to the end. Second, end. Oh, end. I need to get to the beginning. Second, beginning. Oh, that's fun. You're welcome. And then you guys know the insert button already, right? You know second insert?
Yes, is right.
But yeah, second front or second end.
What's second insert?
Second insert, if I'm at the front and I need to type something, which I don't, but I need to here, I don't want to overwrite all my crap, so I can do second insert and throw in a 3. Yay.
Oh, wow.
Right?
I've been deleting the whole
Right?
this whole time.
See, I'm trying to save you time. Okay, 7.14159, whatever, I don't even know. But this one, D. Is that better?
Yeah, that's right.
Sorry, guys. I can't believe I didn't read fourth quadrant. I read it and then I forgot it promptly. Okay. Didn't someone say 10?
Yes, and 11.
Okay, we're just going for it.
Yeah.
So the whole
Basically, we just don't like these.
Yeah.
But wait, our calculator is meant to help us. So hang in there.
Doesn't even help.
Wait. You just got to learn how to use it. Some of you didn't know how to insert stuff a second ago, but now you do. Yay. Okay, so you're welcome. I'm going to my calculator, my calculatrice, my calculadora, for whoever wants whatever version of that. What do I have in this equation? 1 minus, oh, I just have 1, right? It's a limaçon. I have 1 minus 2. Is it cosine, guys?
Yeah.
Thanks. I have a limaçon. And I'm going to do zoom standard, and he's right there. Wait, pause. Did you guys see how this graphed?
Yeah, that's the last part.
It starts here, 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 right? How do I know pretty quickly that pi over 3 is kind of important to this guy? He's a 0. I said it equal to 0, cosine equals 1/2 at pi over 3. Okay, so there is some math to it. I have this little dude, I have my little limaçon. I want to find the area outside the little loop, but inside the big loop. Is this what it did?
Yeah.
Okay. And I know that my zeros are at pi over 3s. Because cosine equals 1/2 at pi over 3s. Outside the little loop, but inside the big loop. You guys see what I want? How do I do that? Didn't 2 pi get the whole shebang? Who don't I want? I need a little loop. Well, where'd the little loop even happen? Didn't he go from 0 to pi over 3? Because that was only half. Or, yeah, I was getting there. Or, so you could think of the big one minus the little one. Or, it's all one graph, isn't it? Couldn't I just show him 9 minutes? Okay, I just hit myself. Wait, guys, this was 0 to pi over 3, right? And then it was like boom, 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 like he's his phone. And then 5 pi over 3 to 2 pi.
Yeah.
So couldn't I just go everything in between pi over 3 and 5 pi over 3?
Okay, see, I did that.
Because from 0 to pi over 3 is 1/2 the loop. From 5 pi over 3 to 2 pi is the other half of the little baby loop. And then I have my 1/2. Okay, sorry, Maggie, you were saying you did that, but?
Yeah, I just didn't do the first part, so I didn't subtract anything. So I did that, and I got like 8.1 or something, and the answer is like 8.3, so I just guessed because it was closest to my answer.
So this didn't end up being perfect?
No.
Okay, hold on.
Okay, I could
It should be. Yeah, it should be.
I had.
Let's double check the parentheses and everything. Because you would have your 0.5 times, is it 4? I think you were right in your logic, though. Because the 5 pi over 3 is when it hits the 0 again, finishes the inner loop. Big old parentheses, guys. Cosine, right?
Yeah.
Big old parentheses to make the whole shebang squared.
Yeah, divided by 2. Oh, wait. Yeah, you get D. See?
It's supposed to be C?
Yeah, no, I guess D.
Oh, but it is supposed to be D?
No, the answer's C.
Well, outside. Oh. No. It's my bad. I did your guys' common mistake, which is why it's an 8.811 right there. We have time.
Well, yeah.
In your calculator. No. In your calculator. Wow, it's been too long since I did one of these. Let me try to show you what just happened. I'm going to need to zoom in on this graph, though, okay? All right. What do we do? Okay. 0 to pi over 3. True? Okay. Then pi over 3 to 5 pi over 3. True? And then 5 pi over 3 to 2 pi. When doing area, 0 to pi over 3 would have been this area. Yeah? Okay, watch closely, please, everyone, eyes up here. From pi over 3 to 5 pi over 3, we extend radii. But when we extend radii, it is completely regardless of what's going in between. Pi over 3 to 5 pi over 3 just did what? The inner loop 2. And then 5 pi over 3 to 2 pi. So when you do 0 to 2 pi of my 1/2 and my r squared d theta, you actually get the outer with the inner twice. Because from pi over 3 to 5 pi over 3, it's not caring about if there's an inner loop. It's just going for all the area. It's getting all of the area from pi over 3 to 5 pi over 3. And if you had done the whole thing, you would have actually had the inner and then the outer with the inner and then the inner again. Which means when you go from pi over 3 to 5 pi over 3, yeah, you've gotten all the outer, but it just went over the inner. Now, it doesn't have the extra inner, good, because we made the bounds what it's supposed to be, but what does it still have just in nature of how polar area works? It has an inner still. So what do we have to do? Wow. We have to take our minus. Or you can go from negative pi over 3 to pi over 3 if you want to get the whole pedal, or you can get the half pedal from 0 to pi over 3 and double it of your 1 minus 2 cosine theta squared d theta. I should have drawn it and I didn't. I was trying to shortcut it and I'm sorry, guys. Ow. But polar area, that's why I was shortcutting it, it's my bad. I always draw it so I can see what the area is and then I can visualize how to move, react, solve accordingly.
What if we want to not, like, what if we don't want to take away the 1/2? Then we would just do 2 pi now? Or pi would be, like, so what's
What do you mean?
Pi over 3 to 5 pi over 3.
Oh, yeah. To get the whole pedal, you would have done negative pi over 3 to 5, or to pi over 3. Kathy?
Do you think that it would be better than just like as a precaution, in like these sort of problems, just to like take half of the graph and then multiply it by 2 with like both the
That would be okay to some degree, except even if you take, like if you went from 0 to pi, you would have to take away this inner. So you would have to go from pi over 3 to pi, and then you would have to take the same process is necessary. So it's more precautionary as if, because Kathy is saying you might forget the 1/2, so if you always go halfway, the 1/2 is always doubled, goes away, but the hard part is still there. So it's up to you. If you're messing up the 1/2 consistently, yeah, Maybe just always go halfway and not have to worry about the 1/2, but I don't know if that's more confusing or less for the majority. I don't know, because we're already playing with bounds. Can we try to fit in one more?
Yes, 11. For common area, you add, right?
Usually, yeah. Common area to 4 sine 3 theta.
And R equals 2, which is circle. See, but I don't know what it means, the common area.
Inside both.
Inside both, and I have to multiply by 2 or what?
Mm-hmm.
Oh, then maybe I got it.
If it wasn't frozen, I totally would then. I'll wait and see if I can catch it back up again. I'm just looking at my bounds really quickly. I'm going to change my window real fast to pi and just see how much of it graphs in pi. So I have 1 petal, I have 2 petals, I have 3 petals. You guys see that I'm halfway through my circle and I'm all the way through my 3 petaled rows? And that's just by playing with my window. Okay, so to help me, is that fast enough, bud? Okay. It's okay, it's just frozen again. All right. There we go. So this guy has 0 to pi period to get all 3 petals. And this guy has a 0 to 2 pi. When I'm graphing, is he still up there? Oh no, I want my graph.
For 11, you use
Do you see how, Maggie, this is what I want, but times 3?
Yeah.
Okay. So then, check it. If we go to the circle, right? Do you see how we're going to have too much? And then if we go to the rows, we're going to have too much also. So what I need, technically, and I think the best way to do it is just to erase. What I need is to the rows first, to the rows up to there. Then I need to the circle from there to there. And then I need to the rows from there to there. Because the circle would be straight, it wouldn't be curved. I need the rows to get me the curve, the circle to get me the there, and then the rows to get me the there. What would I use? I would use intersection points.
Okay, and those are, I just add them and they both have the same.
And I would take this and either all of that and that, or I would take this and halfway and double it. So I'm going to play with that right now while Riley and Deba go check with Mr. Miner and see if they can come back to do the video. Ari, you're checking with Richmond. And I'm going to try to finish this one on the video. Sound good? Okay. And the intersection points, I don't know if they're easy or not.
You look like a bum right now.
What was that, Riley?
I said,
Ooh. Ooh. Yeah.
I just want to say, like, I'm sorry. For, like,
Oh, wait. You have nothing to apologize for. I was literally just amused. I was so amused as far as the timing. But
I feel bad for not, like, paying attention, but, like, I'm so sorry.
I sit next to this girl, in church almost every Sunday, or at least very near. Maggie, how do you pay attention in sermons?
I draw.
On people, on notebooks, on herself, on people. And this is how she listens. Don't worry. There's no judgment. None.
Do we have like a reteaching of this lesson? Because honestly, I have no clue how to do these. These are so hard. These like polar areas that are like minus area of 1.
Let me see if I can find either some good tutorials or, I mean, we technically have some free time, depending on our mock APs and questions. So yeah, maybe we'll continue tomorrow with polar. So I think we have more questions. So right now, kiddos, I am finding the intersections between my 3-petaled rose and my circle, literally using trig. And I know it's hard, but if I was to zoom in on, once again, this petal and make it so accentuated that you guys can tell exactly what's going on, and then this circle from the origin. If I was to draw those radiuses like I was showing you, the radius to the rose literally goes and hits from the pole out to the rose up until this intersection point. I need this curvature right here for this area that I'm trying to find. But then, starting at that intersection point, starting at this angle line, I now need to extend to my circle. But that's only going to work up until that sector, that part of that circle only works up until this intersection point, or I should say, if it helps you, this theta line. What we just found is that this theta line is going to be theta equals pi over 6. And then this theta line, this next intersection point, not pi over 6, lo siento, pi over 18. According to these points that I found over here. So I have pi over 18. This one is going to be theta equals 5 pi over 18. Oh, and that line down here is very nasty. I apologize for this line being kind of off. But I think also my drawing was a bit off. Let me see if I can get a prettier line. So there's my theta equals, and then here's my theta equals. Give me 1 sec. So then before pi over 18, it's purple going to the petal. After 5 pi over 18, it's pole going to the circle. And then once again, after 5 pi over 18, I need to go back to that rose again, which we could figure out what that is by then figuring out when the rose completes. If the rose completes in 0 to pi, every petal takes up 1/3 of that space. One petal should take pi over 3 to complete. So I could go ahead and have the ending of this whole situation be theta equals pi over 3. So one way of doing this problem would be a big old 1/2 here out in front, just for everybody. And I can go from 0 to pi over 18 of my, can I just name these? We're going to name him R1, name him R2, which would make things easier for typing in your calculator anyway, to name like one of them Y1, one of them Y2, etc., or R1, R2. To my rows would be R1 squared, plus, now I need to go from pi over 18 to 5 pi over 18 to my circle, which would be R2 squared. Then to finish this guy off entirely, I could then go ahead, let me try to fit this in one line to make it simpler. Come on. Never mind, I won't do that. Here we go. 5 pi over 18 to pi over 3 of back to R1 squared. The other way of doing that is you could do halfway, like Kathy was saying, halfway and doubling, using that symmetry, but the halfway, you would only need one part, that first purple part over there. So 0 to pi over 18 of R1 squared, plus, but you could only go halfway of the circle. because you would want to cut this region in half. And so halfway between pi over 18 and 5 pi over 18, there's 4 pi over 18 in between, 2 pi over 18, so that'd be pi over 18 to 3 pi over 18. And guys, there's already been so much polar area understanding necessary in this problem. I hate throwing this at you, but even if you plug that into your calculator, you would be wrong, because they said inside area common to the whole polar curves. Meaning, I've only done a third, because there's a region there that's the same and a region there that's the same. So therefore, right down here, when we found this, this was only for one petal. So if I wanted to make it for the entire region, I would need to multiply this guy by 3 to get the 3 petals. I would need to multiply this guy by 3 to get the 3 petals, or the 3, I should say the 3 regions that are in common or common to all. Now technically, kiddos, on the AP itself, we're just going to watch this tomorrow real fast so everybody sees it, because I doubt most of you will check it online tonight, and I think this will help. On the AP itself, these problems do take time, so might be a strategy to pass over the polar area multiple choice and come back to them as far as how much time they could take. But that's going to be personally up to you. I'm going to go ahead and quickly throw this into my calculator since Deba and Riley walked out, and I have a little more time. I'm going to go ahead and do the simpler version, which I think would be 3 times the 1/2 times 2. The secondary version just looks easier to plug into my calculator. I do have, just double checking really fast, R1 as my 4 sine 3 theta, R2 is my 2, just double checking that's what I have here. R1 is my 4 sine 3 theta, R2 is my 2. Okay, so then I can go ahead and do my pi over 18, and then pi over 18 to 3 pi over 18. So I'm going to go ahead and do 0 to pi over 18. Love that my calculator can do that. That's pretty cool. I'm going to do my alpha vars. Pretty awesome. They're r's because I'm in polar mode, so my r1 squared with a d theta. And then we're going to add from pi over 18. Remember, only going halfway, so 3 pi over 18, because that's symmetry I'm doing, of my r2 squared. I'm not showing you my buttons, and I apologize. The glare is kind of in my way. Of d theta. And then all of that is being multiplied by 3 to get my 3 petals. The 1/2 and the 2 canceled out, so that's why there's not a 1/2 in there. And I believe my final answer should be 4.91374. 4.91374. It looks like their rounding is off, but I'm really hoping they just truncated instead of rounding, and the final answer is E. We will see tomorrow. Bye, guys.